Right. So, Guillaume, do you want to say something about the coursework on record now that we are recording?
On the record, yeah. So as I was saying, we have a target deadline of week 5. You may, if you need more time, you can have more time. But the thing is that then you will have the second coursework also to do, and you will have your projects that you need to put together and so on. So it's better to start early and do the stuff you can already do, and slowly every week during the 1 hour lab, just do a couple of questions, and then you'll be fine.
So, what day of the week in week 5?
I think we are week 3 at the moment, right?
Yeah.
So it could be towards Friday, is it Thursday maybe, 20th or something?
The 20th?
Yeah, that's a good target, I think. And as we said on the first lecture, right? Originally there were 3 hours of lab plans, but in our experience it's not needed, like people just don't show up. But if you do need extra hours of lab, just send us an email and we can schedule some additional ones. Actually, they're already scheduled. We can just show up to the lab on that day.
Yeah. So Saturday, 15th of February doesn't exist.
Yes.
Okay. Anything else on the admin side we should do before? No? Okay. So I understand you did equality last time. And was this a cliffhanger because you ran out of time or because it's hard?
No, the above that, so implementing
I see.
symmetry and transitivity in terms
Yeah.
of subs.
Okay.
There's a cliffhanger because I think it's a good thing to think about throughout the weekend. Right?
Yeah. And that's what cliffhangers are. Yeah. Okay, so let's see if we can do this. So I'm just going to state what symmetry is. So it's saying if I have 2 elements of some set X, and I know that X equals Y, then I would expect for Y to equal X, right? So it's symmetric. I can swap the 2 orders. Okay, and of course, yeah. Right, so let's do this slowly. So if all I wanted to do was implement sim, then I would normally just pattern match on this P to see what it would possibly be, right? And if it's raffle, then I see that my goal is easy and I'm done. But if I don't want to do that because I'm interested in how things fit together, then I could try to do this in terms of subst, which if I just ask for the type, you get something horrible from the standard library.
Beautiful from the standard library.
If I fully normalize this type, so control U, now I have 4 control U's, but I think that's fine. Control C, control full stop. Well, I guess that wasn't fine with 4 control U's. 2 control U's. Then you still get something a little bit scary, but at least this strange part at the bottom disappeared, right? So we have a bunch of implicit arguments which says that, okay, we are talking about arbitrary sets A, and they are at arbitrary levels. And we have arbitrary properties P, which are at arbitrary levels. So the level is the size of the set. We're doing our best to ignore this. And then the interesting thing starts really here down on the last line, right? So here again, we're saying if I have X and Y, and sub says if now X is equal to Y, and I know P of X, then I also know P of Y, right? So any property that holds of X also holds of Y if X and Y are the same, which is very sensible, right? And it's called subst because I'm taking this property P and I'm substituting Y for X here, right? So I know P of X, I know that Y is the same as X, so then by substituting I get P of Y. That's the idea of the name, right? And the implicit claim is that almost anything you can do about equality, you can do just with subst. So subst is implemented by pattern matching on refol, and then anything else you could just use subst for if you wanted.
Yeah, the hard part is picking the right predicates.
But then you have to pick a P, right? Okay. So I know what to give as the argument of X equals Y here to subst. That's my little p, right? because I have one proof that x equals y. So if I do that and ask for the type again, I need to give a predicate, okay. So I put a question mark for the predicate. I don't know what that is yet. I give the p, and then at least my type is a little bit less scary, right? It's saying that if I can show this question mark for x, then I get this question mark for y, right? Now I have to think of a predicate so that I can show it for x, and when I instantiate y for it, I get what I want. So what I could try to do, I look at the goal, and I say, okay, what can I kind of abstract from this to get what I want? Well, if my predicate is to be equal to x, then in the end, I would get the goal that y is equal to x, which is what I want, right? So I could try this. Okay, so here's my predicate p. It's a predicate which, for z, gives me back the statement that z is equal to x. Okay, and if I see what I get if I have this, x is not in scope, so I will introduce x in scope, and it should come before the p.
Yep.
Because it comes before, this is my p. So let's put it here, I reload, I try again. Okay, then we see that subst says if I can prove my predicate for x, then I get it for y, right? So for x, my predicate is that x equals x, and for y, my predicate is that y equals x. So that's very good because this matches the goal, and this is also very easy to prove, right? So just leave a question mark for that final thing, and then I see that what I have matches what I want. Excellent. Reload the file just in case. And I look at the goal, and I see that reference will just fit here. Okay. So all the pieces are easy, but really, as Guillaume said, the tricky thing is coming up with the right predicate here, right?
Yeah. But maybe I can give you a few clues about how to do that. So the type of subs is really helpful. This this fact that we're parameterizing over some p that computes the return type is actually really helpful because it says, I'm telling you how to make use of some equation to solve whatever problem is in your face. So you should read the very return type of subst, that p of y, as whatever problem is in your face that's talking about y. And how Fred got this thing here was simply to look at the goal and abstract all the occurrences of y. You literally just take the goal that's in your face and do, actually, I would have just done lambda y. I would have left the goal alone rather than replacing y by z. But there was the goal that was right there. It said y equals x, abstract over the y. That's your problem that is in the return type of subs being solved for y. That's progress. It's we should not overinflate the difficulty of constructing these capital P things.
Yeah, we're talking about predicates, which is a very semantic word, right? But then when we're actually building one, it's a very syntactic process. We're just looking at the goal and all of the y's we want to turn into x's, and that's the ones we capture with this lambda z. There could be other y's somewhere in the proof, right, which we don't want to capture, and then the z will only replace the ones that we want to modify into x's. So it's a very syntactic process when we go around and build this P.
Okay, should we try this syntactic process on the next goal then? So
yeah.
I've stated transitivity of equality. So if x is equal to y, and if y is equal to z, then in one step x is equal to z, right? So we're putting two equality proofs together. So, okay, let's try this process. So the first thing to think about, so now we have two possible equalities we could give to subst, right? But let's be simple-minded and just try the first one first, right? So then again, we would do subst something p, and then we see that we get to go from the goal where we have an x to the goal where we have an y. And what is the goal now? Well, it would be the rest of this.
Yes, introducing Q was not helpful.
Yeah, so let's see what happens. So I could do what Connor suggested and just call this y and copy it right in. And then we see that the goal we have is good. If we apply it to a bunch of things.
There's something very strange going on here.
Except it's the wrong way around, right?
What's happening with this goal?
Oh, is it because this
I'm trying to understand why the goal is y equals z.
Right.
That's okay. That's more like it.
Right. Okay, so I didn't reload for some reason. I mean, I guess that's it. So when I first typed in trans, then I had a typo here and I had y. Okay, so now the goal matches. We have two sub-goals. So here we have to deal with the case when they are the same, right? So we have to say if x is z, then x is z. Okay, that is easy. And here we have to give a proof of y equals z. That's the Q. So if we wanted, we could not introduce it on the left and not give it on the right. Okay, so the method kind of worked. We just took the remaining goal, put that as our predicate, and then we were able to deal with it in the simple setting. Just like we were able to deal with it when the proof P was REFL, right? So what we're doing here is kind of the same thing as when P is REFL. Okay, does that make sense?
So this is a really good example of something we were talking about last week. This code is absolutely unreadable, and your only hope of understanding what is going on is to punch holes through the term that is used in the right-hand side and look at the types and figure out how it's working. So it might take actually a lot more time on paper to figure out what is really going on if you want to add all of the implicit arguments and so on to really get a feel for what's happening here.
Right. Also notice I was a little bit sneaky when I set this up because I know that when I use trans, I want to keep these x, y, and z implicit because it would be annoying to give them and they can be inferred from these arguments. But I already had a feeling for that when I was going to state my predicate, I was going to mention y and x and so on and even z, right? So I made sure to introduce them here on the left as explicit arguments locally when I did it. So that otherwise I couldn't mention them here, right? Okay, does anyone else want to do the next one or should I continue? Connor?
So what am I supposed to be doing? Showing that
Leibniz equality and ordinary equality is the same.
okay. I don't know how this. The main challenge is, of course, to use a keyboard that isn't mine. I'll just attach this mic. Okay. So I want to prove. Well, what do I want to prove? I want to prove that x is Leibniz equal to y. Okay. Thanks very much. I'll normalize that to see what I'm really trying to prove. I'm trying to prove something which looks an awful lot like the statement of subs. but okay, fine.
Did you explain the term Leibniz equal last time?
Yeah, we did. I mean, so
Yeah,
the philosopher Leibniz characterized equality, what it means for two things to be equal. It means that anything that's true about one of them is true about the other one. So that's what we're saying here, is that for all properties P that might pertain to things of this type, if the property holds for X, it holds for Y. That's what X equals Y, it kind of morally means. Okay, so I will introduce this P, and this, actually, I will even go as far as to name this PX. Let's see what we've got. Right, so you see there's some property capital P, and I know I've got a proof of that capital P holds for little x. I want to give a proof that capital P holds for little y, but what was subst again? Oh, what's it? I've got to do
Taking
it.
the predicate.
Oh, Evans. Right, so subst is exactly saying that. Oops, px. Okay, so there we are. I mean, what we're basically, so Leibniz basically said, equality basically says, the equality that does what subst does, right? So it shouldn't be a surprise that that subst does that thing. Okay. And now what happens if I want to go the other direction? Let's have a look. I know that x is Leibniz equal to y. If I normalize everything in sight, I get a very handy fact. And I see this universally quantified P that is used in the return type, and I think, fantastic. This, this is good for solving all sorts of problems. This is just saying, what's the problem that you're trying to solve here? You got a problem that talks about y, turn that y into x. Well, I do have a problem that's talking about y, so I'm going to just go, because I can't type Unicode, so you tell which bits of these things are by me. I can operate Emacs. I literally grab the end, actually I should have I picked it up from there, but you can see it's the same as what the goal was. I paste it in there, and I say, what have I got now? Oh, and then of course I need X to be in scope. That's okay. I'll bring it into scope. And now it says, oh, I've got a proof that X is Y, provided X is X. So I'll take that, thanks. Put that in the hole, and now the problem is to prove that X equals X. But hey, that's raffle. I'd better reload just to make sure that everything's colored in a non-offensive manner. But yeah, this is cool stuff. So yeah, I don't know if you remember back in semester 2 of first year, somebody may have taught you natural deduction, and they will have taught you that proof goes from assumptions working forwards.
You know this, and then you can use some rules to deduce that. And you then encounter the rule for OR elimination. All of a sudden, you've got some A or B, and all of a sudden the rule starts talking about this thing called C. It says, oh, if you can deduce C from A, and you can deduce C from B, you can deduce C from A or B. And you sit there thinking, how the hell do I come up with C? I mean, what a confusing rule. And the point is that the game was lost when they told you the proof goes forwards. It doesn't. It goes backwards. The C you need for disjunction elimination in natural deduction is the thing you're trying to prove. It's whatever it is, whatever goal is in your face, you substitute that for C. It's the same thing here. Don't overthink, like, how do I choose big P? You instantiate big P to the goal that's in your face. The fact that the thing offers to solve any goal is wonderful news. You don't have to spend a miserable time thinking about what it ought to be. You can see what it ought to be. It's the very thing you're trying to prove. As long as you realize that you are in fact allowed to look at the question before figuring out how to answer it. Who's next?
Cheers. Yeah, so here we've been writing functions going back and forth between our notion of equality, propositional equality, and Leibniz's notion of equality, which is characterized more in terms of the observations you can make of the values. But what's really important in what I just said is that we are going from one type of proof to another. We're writing functions that we're turning one kind of proof into another. And this is a really deep parallel that you can build all the way between sort of functions and their types on one hand, and logic and implications and proofs on the other side. And now for the rest of the hour, maybe a bit tomorrow also, we're going to be looking at this principle, which is known as Curry-Howard, which allows you to use the type system that Agda gives you, which you might think originally is only to write functions from nat to nat or whatever, to actually prove statements. Well, first, form statements, and then hopefully be able to prove them by applying deduction steps, which are nothing but functions that you can use. So functions, programs, and proofs are essentially the same, and theorems like statements and types are also the same. So you have this sort of parallel. So going back to what we're seeing on one of the very first lectures, we looked at these two facts. So we had 1 plus n equals n plus 1. And we said, well, we tried to prove this using REFL, and it didn't work because I couldn't see that they were exactly the same on the nose. But then we saw a proof by induction that these two things are true, right? We said, well, if I take n apart, I can actually justify both a base case and a step case, reducing the statement to a simpler one. So this was not provable using REFL, but it was actually provable using a more powerful proof principle, which was induction. However, we saw something else on that day, which was also not provable by REFL, even less so by RELFL. Which is the statement that 17 equals 42. But here it's even more fundamentally not provable than the other one, because the other one we could actually prove it using a stronger proof principle, but this one will always be false. And a way to express that is to introduce a type that you cannot build elements of. So this type is telling you what the fundamental notion of being empty or being completely false is. So we usually, sorry about the Unicode, well, I even cannot type it, call it bottom. Yeah, of course, this is not going to fly. Yeah, otherwise it creates a meta and it's annoying. Yeah. All right. So what am I doing here? So if you remember when we saw simple inductive types, we said that data was introducing a new type constructor, and then we had potentially a description of the arguments it could take. Here it's called bottom, and it's not taking any argument whatsoever, and it's a type. And then we're saying where, and we're listing the constructors.
Yes.
And the constructors are ways to build values of that type. But of course, if we want to express what it means to be empty, or to be the essence of falsity, there's no way to prove that falsity, and so there shouldn't be any constructors for it. So this is actually like the full definition of the empty type, right? It's saying we have bottom, but by the way, there's no way to create it.
Yes. It comprehensively listed none of the ways to make values in the empty type. The traditional mathematician joke. Yeah, I've eaten all my children, all the ones I know about.
And so now we can express what it means for 17 equal 42 to be a completely absurd statement. It's to say that, well, if you give me a proof of that statement, I will give you a value into the empty type. But there's no way to build values in the empty type. So something went wrong if you were able to call this function at some point. And Agda has a really cool mechanism for that. So just like we have REFL for things that are trivially equal to each other, we also have this empty pattern. So this is a lambda, but instead of naming the variable, I'm saying, look, this is a lie. There's no way it could be inhabited. So I put this pattern, Agda comes back and says, yeah, okay, that's fair. 17 will never be equal to 42. This is a valid proof that if someone hands you such a value, you can do anything you want.
Yeah. There is something to say here. It's a kind of bitter irony / cruel joke on Haskell programmers that in Haskell, empty parentheses mean the boring value in the unit type, whereas here, empty parentheses mean the impossible pattern in an empty type. So that's also good news, by the way, is that there are two ways to write a program in Agda. One of them is to say what the output is, and the other one is to tell the input to go away. And that's what we've just done here. You claim to be a proof that 17 is 42. Go away. And that's deeply simple.
So Haskell is an extension allowing you to write these sort of like empty matches. It's but you're not really supposed to write this sort of empty types. It is convenient sometimes, though.
Is it worth doing the pedestrian way to do this without special support? Could be fun, maybe. Subst.
Yes, okay.
You want me
Okay.
to do, you want me to do it? Or do you want
Yeah, sure. Maybe do it for 0 and 1. I don't know. Yeah.
Well, I think this will still work. So.
Oh,
another
by
way-
recursion. Okay.
uh,
Oh, sorry. Yeah.
Yeah. So if we don't know about this special support that Agda has, then we could also try to do this with the tools we do know about, right? Because we want to get something out of an equality. Subst is a way to get something out of an equality, right? So if I do subst, oh, am I allowed a where clause in an anonymous thing?
Oh, I don't know. You're pushing the limits.
I am.
Nice.
So if I do subst p and then then I would like to give this proof Okay, I'm just going to name this.
Oh, lambda binded, yeah.
Lambda. Okay, so now P here is my proof that 17 is 42. So I give that here, and then I want to go from P of, then I get to go from P of 17 to P of 42, right? So I better make sure that P of 42 is empty. Say that. Okay, let's make this more than numbers, because writing Saga says 42 is just a shorthand for suck of 42 times, right?
Can you write 17? Is it small enough that you can do it sort of backwards?
Just going to change this to 1 equals 2.
Okay.
Because I think it goes up to 10 or something like this. So I can say that P of 2 is empty. So then here now, if I can do this for n equals 1, then I go to empty. So I better make sure that I can give a proof of P of 1, right? So I'm just going to say that P of 1 is the natural numbers, say. And then I also have to say what this is in general. I don't really care. I only care about these two cases. So I'm going to say this is the natural numbers again, I suppose. Because now, if I only can come up with some natural number, then I get the proof of false. So the claim is, if 1 is equal to 2, well, then we can substitute 1 for 2 in anything. So in particular, we can go from something inhabited to something uninhabited.
So the key thing that happened there was that we wrote some program that looked at the number and said, but you know, I can actually write a program that tells 1 apart from 2. So 1 can't be equal to 2.
And another important thing to observe is that we've written a program that actually computes a type, right? So this is taking a natural number and it's returning a set. So far, all the one we've seen were really boring. We're saying, okay, lambda x equals y or something as the predicate. But here we're actually performing some computation in the type. We're performing some computation on the natural number to decide which of the types we're going to return. So this is an extremely powerful principle that you can use to write a type-safe printf, for instance, because the string is telling you exactly what sort of arguments you're expecting. Okay. And so, so earlier I was saying that when you write, if someone gives you a proof that 17 equals 42, the fact that this statement is proven, so 17 equals 42 implies the empty type, means that if someone hands you such a proof, you can do whatever you want. And what does it mean to be able to do whatever you want? It's the so-called explosion principle. So if you have a proof of the empty type, then you can get a proof of anything you like. So you get to pick this A, arbitrary A, and you will always be able to produce a value of that type. Of course, the idea is that because it's impossible to build such a value, all of the branches in which you will get your hands on the proof of the empty type will be sort of dead code. And so you can exploit the proof of the empty type to dismiss the dead code branch and say, yeah, it has the right type, whatever, because it will never be reached in practice unless your type system is deeply broken. And how do we do that? Well, we introduce, I've been walking in the minefields without knowing it. We introduce this value, so now it's in the context. And what do we do when we have inductive data? Well, we can challenge Agda to tell us how it was built. So here you're claiming you have a proof of the antitype, well, I'm going to case split on it, and you better be telling me that it's impossible. And so now we have this new top-level error sort of combinator, except that it's a safe error combinator. We know for a fact it will never blow up in our face at runtime.
Yeah. So this is the thing. You're used to functional programs that consist of equations, but AGDA programs have equations and refutations. There's no equal sign and there's no output, because instead of saying what the output should be, we're explaining that why the input's impossible. We're telling the input to go away. This can't be happening to me. I don't really have to come up with an element of type big A.
I mean, on the other hand, it's a normal function that takes every input and turns it into an output, right? Just happens that there are no inputs, so there's nothing to do. But
so just like REFL gives you trivial equality between things, this pattern gives you trivial emptiness. But sometimes emptiness is not quite trivial. So I haven't tried this, but I think it shouldn't be the case that AGDA will allow us to say, well, it will let us say that plus is not equal to times, but I don't think it will prove it automatically. So let's see, I'm going to introduce the equality here, reload, look at the goal, and then try to split on equality. And I'm getting the dreaded error message saying, well, I was trying to make sense of this thing to see whether the equality could be built using REFL, but I'm not sure. They're just too different from each other. I have no way of like either telling you that it's impossible or finding a way to make sure that they are equal to each other. And of course, there is a way to make sure they are equal to each other. Oh no, that's the wrong one. No, what did I do? Oh.
if they are equal to each other, then 1 plus 1 is the same as 1.
Yeah, so this is why I wanted 0, 1. Okay, let's do 0, 1. And let's name it. It's 0 is not equal to 1. Okay, so now we cannot dismiss outright this possibility because I just cannot see that it's impossible. But we can use a more specific statement, which is obviously impossible. And as long as we can reduce our inputs to a proof of this obviously impossible statement, we will still be able to prove that the branch is impossible. So I'm saying, okay, I'm reducing the problem of proving that plus is not equal to times to the problem of proving that 0 is not equal to 1. And of course, it's the wrong way around now. Luckily, we've proven symmetry, so I can do symmetry. And then, oh, it's not imported. Let's pretend we had imported it already. What are we going to do? Well, in the context, we have this assumption that plus is equal to times. And if you remember the definition of congruence, it's telling us that if we do the same thing to the left-hand side and to the right-hand side, if this is a valid equality, then the modified left-hand side and right-hand side will also be equal to each other. And so in particular, we can say 1 plus 0 is equal to 1 times 0. We're just slotting in 1 and 0 in the same position on both sides of the equation. So if plus equals times, then it should be true that applying them to equal arguments will yield equal values. I'm doing, this is a bit tricky, 1 and 0 as said. So what am I saying? If you look at the left-hand side here, its type is nat to nat to nat. It's a function taking 2 arguments, right? So when I'm applying congruence, it's giving me either of the sides, the left or the right-hand side, and then I want to transform it. So I'm passing the 2 arguments explicitly. This is why I'm getting a function here, because there was a function on well, the equality is talking about functions. And then I should just be able to pass the equality, and that gives me a proof that 0 is equal to 1. So sometimes you have something in context that you see is absurd, but Agda doesn't see is absurd. So then you need to do a bit of work to reduce the very general, potentially absurd statement that you have to something more concrete that Agda will then be able to say, yeah, okay, that's fair. It's impossible.
Yeah. So proving, or rather, yeah, disproving an equation is always a case of coming up with some sort of observation that pushes the two things apart. You know, what test makes it obvious that these things don't behave the same way? And Agda can come up with those sorts of tests for things like telling different constructors of the same data type apart, but it's not much cleverer than that. So sometimes you have to cook up the observation that's going to drive things apart. And in particular, the thing which turns it from some weird problem about functions to just knowing that 0 and successor are not the same constructor. So that's, we've done a function, we cooked up a function which transforms a difficult equation to disprove into an equation that's obviously false.
Does someone want to do double negation elimination?
Double negation elimination. Why would I want to do that?
Well, double negation in general, you might want to introduce it.
Uh-huh. Well, okay, we haven't said what negation is. So let's... right, so let's have...
Oh, yes.
Ah, yes. What do I do? Do I click on fra
Yes.
and get a keyboard from an island that I'm not from? Right. So, we're interested in, if we think of X as some logical statement, if we want to cook up the idea of what it means for X to be false, the suggestion here is that we can define the logical negation of X as being functions from X to the empty type. As remember, in Agda, a function is a promise. Right? So if I'm able to write this function from X to the empty type, there better be no such thing as an X. Otherwise, you could feed it in to my function, and my function wouldn't know what to do. So this is a reasonable way to encode what it is for. What we're really claiming is that X is an uninhabited type. We should check, for example, that we can prove not false.
So what we're saying is that not X is true if X is less true than false. Right? But whenever X is true, then false is true.
So this is kind of nice. I'm trying to prove not false, and that's a function from the empty type to the empty type, and fortunately I know such a function. The identity function will do just fine for that job. You know, whatever input, it might take a while to turn up, but never mind. If it did turn up, we would just hand it straight back as the output, and that's kind of nice. It's also the case so let's have double negation introduction. If we've got an X, some set X, and somebody gives us a value of that type, then we ought to be able to prove that not X is false. Yeah? Does that seem reasonable?
You know, we really hope that if X is actually witnessable by some piece of evidence, that not X is not provable. So, okay, not X. Let's look at that. It says someone's actually going to give us a proof of not X. And now we have to prove false, which is never a good situation to be in, except, of course, that, you know, some foolish person has said they can turn X's into proofs of false, and we're going to call their bluff by just applying that function to the evidence we've got in our very hands. So yes, you can prove double negation introduction. But what do you think?
And if you take a look at this and look at its type, the expanded version, right? Because we're taking two arguments, even though there's only one here in the type. It's because we're grabbing the not X and pulling it across, right? Because not whatever is a function. So this is saying that if you give me an X and a not X, I can prove false. So this is also sort of absurdity, right? The usual logical construct telling you that you can conclude anything from a proof of A and not A at the same time.
Now, you know, once upon a time when you were in first year, maybe somebody taught you some kind of electronic stuff involving like NOT gates and things like that, and they may have told you that if you have two NOT gates in a row, you can just get rid of those things. That's just expensive wire, right? Well, it's true for the Booleans, but is it true in general? You know, if we've got two knots, can we just get rid of them? All right. So, yeah, what do we got? We've got something that said, well, if we had conclusive proof of the non-existence of X's, we could blow up the world. Does that mean we know how to build an X? I mean, this is basically saying that when the absence of something is unthinkable, we actually know how to make it. No matter what it is. Right, so that's the thing, is that these sorts of logical statements, when we move them into this computational world, they mean something altogether more tangible than they do in the kind of more mathematical world. You know, this thing really says, I know how to output a value of type X. Right. I actually know how to compute it. So, for example, well, we got the. I mean, like, so when you've got a value in some either type, remember either in Haskell? Yeah. So that, you know, when we do the same thing in Agda, we're really promising to come off the fence and decide stuff one way or another. You know, it could be that that we choose a type X where values of type X are made from actual bits, and when we write this type, we are promising to hand over those actual bits, and the fact that we've got some negative information is no help whatsoever in coming up with real bits. So that's a distinction that shows up here, which doesn't show up in kind of ordinary mathematics, where people wander through life not being able to tell real bits from magic bits. In AGDA, there are no magic bits.
So one problem if you try to implement this is that there's really two different situations, right? If you could decide if x has a value or not, then if x has a value, then we could give that back. But it could also be the case that x doesn't have a value, in which case this not x is impossible, right?
Yeah. So yeah, if we knew whether X was inhabited or not, we would win this game.
But if we don't know that, then we don't know which one of these two strategies to pursue, right? Should we try to produce an X, or should we try to say that what we give them is nonsense? Because if X is empty, then this says that empty goes to empty implies empty. And empty goes to empty is easy. That's the identity function. So this says we have an element of the empty type, which means that the input was impossible. Right? And that's very different to pursue that strategy compared to the strategy where we try to come up with an X. So the problem is we don't know which one of these two cases we are in, so we can't implement this function.
Yes, which is one of the reasons why when I used to teach Boolean logic to first years, I was always very particular to try to limit the scope of what we were doing to the testable. So when you're working with Boolean signals that are represented on wires as sort of 0 volts or 5 volts, then there's nothing you can't find out with a voltmeter. If you're actually in a position to test stuff, the world gets a lot simpler. But if you're not, then you have to think things. Computability is just a fishier, a murkier game than mere testability, and that's the thing to get used to. What's next?
I think we stop.
We stop? Sounds about right.